1 2 1 2 1 2 1 2 1 2. Woo! Subsequently, as we look at if a tree is balanced. Now, getting to the bone of contention, which is the is balanced value, check, looking at it on a node. Now we say if a node is none, return true. So basically, we are saying that if a node that is none is actually a balanced node, right? That's what that resolve is right there. So we now look at and that's our base case, obviously, because obviously we are going to be hitting nones. But yeah, we call our left and our right, and we call get height on it. So basically for this illustration here, let's say we're making use of this balance. So now we call the left and the right, and we get height on it. This will give us a height of 1. This will give us a height of 0, obviously, right? And then we check if the absolute difference if it is greater than 1. So why do we use absolute here? It's quite simple because say the left is 0 and the right is 2, right? What we're going to be having is minus 2. So that absolute helps us return a positive integer while we find our difference in no matter the direction we come from. Now, so if it is greater than 1, right, we merely know that the tree is what? Is not balanced, so we return false. But if it's not, then we go ahead to call is balanced again on the left and on the right node, because I said we are looking if a tree. If we're looking at if a tree is balanced, not if just the node is balanced. So this guy could be balanced, but this guy over here might not be balanced, right? And we could see that by let's say we are looking at this balanced tree right here, and we come here and take away this guy. So we take away this guy. So our tree still remains 1, right? Our height, the height of this node now, let's say we've already established that this node at this point is balanced, right? Because the height is 2 and the height here is 1. Now imagine if we did something where this guy is no longer here, and then if this guy is returning a value of returning a value of how do you say 0, right? This was returning a value of a height of 0 right here, and then we'll compare it in this recursion to return us 1. So this will give us 1 eventually as a height. So you imagine if we had removed this, and then so that would mean what we have here would be it should still be 1, because obviously we are the height of the tree is basically which is greater between the two of them. Now imagine if we had this 3 somewhere over here. Sorry. So imagine if we had 3 over here. Okay, put this up. Okay, let me see if I can just pick this guy out. Yeah. So imagine if we had it over here, right? So now, and then we had that over there, and then we also had something over here. We also had maybe say a 3 over here as well. Sorry. So we also had a 3 here rather than a none, right? So now automatically this becomes, right? This becomes 2 and this becomes 3, right? Because we now have 0, 1, 2, 3, right? And basically our star gives us 0, 1, 2, 3, and then we are now like, okay, is this balanced? Now when we look at this guy at this top node, yes, it is balanced, right? This guy is balanced. It works because the difference in height is 2 and 3. But now when we come down to this node here, it's not balanced, because what do we have? We have 1 here, we have 2 here, right? Because we have 1 here and we have 2 here, this guy now returns here 2, right? He returns here 2 because we have 0, 1, 2. But this guy here returns what? 0. So immediately we see that the tree holistically is not balanced. The head might be balanced, but the tree holistically is not balanced. And that's the idea we are trying to inform. So a balanced tree has to be probably is it perfect or maybe full by one, but it has to just be, I guess what would we see what it will be is we have to have balanced nodes across every depth, right? So that's how we find the balanced tree.